Okay, good afternoon, Rob, and thank you for undertaking this interview as part of the BioTrib series of kind of conversations, I like to say, between academics both within and outside BioTrib. And I suppose to start off, can you just kind of briefly introduce yourself, give a brief overview of your research career and what your current research interests are?
Sure, thanks, Richard. I did my PhD many years ago, 16 years ago, something like that, at the University of Leeds, and I guess that's why we know each other. And I did my PhD in thin film fluid dynamics, and from there it's kind of evolved into tribology. So I've done a fair bit of tribology modelling, and most of my research is tribological when it comes to thin film fluid dynamics. It's evolved a little bit further. So when it comes to looking at tribological contacts, especially fluid-filled contacts, I did some work on looking at where we've got topography and where we have these patterned surfaces. And that's kind of led to quite a lot of my research, which is now on multi-scale methods. So I do a lot of computational multi-scale methods. Some of that's structural, some of that is still in the tribological sphere. And it kind of means that I've got research kind of from structural mechanics and multi-scale methods all the way up to tribology. I guess my other interest that ties quite a lot of this together is optimization. And I think especially when you've got powerful and efficient numerical methods for solving problems, I think that some of the additional benefit that you can bring to the problem by not just using it for analysis, but using it for optimization is really powerful. And I think, as a general rule, my feeling is that if you've got efficient ways of solving problems, then, throw an optimizer at the problem and see what you can do to design.
So kind of I can remember that optimization has been around for a while now, hasn't it? It's not a particularly new field, but I suppose that the power of computing has changed and allows you to do a lot more with the optimization tool. Would you mind just commenting on that?
Yeah, so absolutely. I mean, optimization in various different approaches, and we're talking about formal numerical design optimization. It's been around for many years, and especially subjects like topology optimization, which we see, exploding because of the advent of additive manufacturing, has been around since the 1980s, when the fantastic optimization group up in Denmark at DTU really did seminal work on this. And you're absolutely right. The additional computational power that we now have means that we can look at extra design variables, extra complexity. And really, it kind of opens up a whole range of new areas. It's fairly well established in the aerospace industry, where, of course, lightweighting and optimum aerodynamic performance is really important. But I think we're going to see, and we are seeing it being applied to more and more different areas. And you can see that bioengineering would be a fantastic one, partly to work out actually what happens within the body using inverse methods. And there's work that's been going on in this related area in working out tissue properties and things like that, but also for improving the life of artificial joints and using analysis and linking really complex and heavy computational analysis to optimization. And that's I guess one of my major interests.
And does this have a role to play in the idea of a digital twin? So the computational design, right from the kind of requirements phase right through to deployment, I suppose. This idea of efficient design and
yeah, and you could see it maybe linking it to different patient groups and using it for design, predicted activities of living that the patients might go through, and then maybe even linking it through to measured activities and seeing how much it diverges and what the predictions are and how much wear and what the predicted lifespan of the joint is. I think there's enormous potential, and I think computational methods, as we start to learn more and more about artificial joints and how they wear and how they perform, I think the potential is enormous.
One of your research foci is the idea of modelling lubricated contacts, and obviously this is a vastly broad field in terms of both automotive, aerospace, but also in kind of bioengineering. And I wonder if you could just quickly describe the tools you use to provide insights into these lubricated contacts.
Okay, yeah, so we use typically a finite difference computational approaches for solving lubricated contacts, but as well as that, we've also used multi-scale methods where we've got a patterned surface, for example, and we have little areas of microcavitation. We also use inverse methods. So we have a paper under review and resulting from PhD student Lee Nissam's work, where he's done some inverse methods to look at synovial fluid properties as measured in a relatively simple sort of ball on plate tribological contact, but where you get really interesting and complex outcomes, and you get this kind of agglomeration of protein particles in the inlet. It leads to an increase in viscosity, it leads to a separation. You get these really interesting transient effects for what would normally be a kind of quasi-static kind of simulation.
Mm-hmm. And this is the paper I was going to move on to that you kindly shared with me. And you get this apparent thicker film. This was first observed by one of your colleagues. Is that correct, Connor?
Yes, this is based on the experimental work actually of Connor Myant and Philippa Cann, who are colleagues at Imperial. And they did some really fantastic and kind of seminal work on measuring the film thickness in a tribometer and using a kind of a biological fluid and looking at how the protein molecules kind of give this thicker, more viscous region at the inlet of the contact. And this leads to an increase in film thickness as it accumulates in the contact. And what we did is we applied some computational methods, we applied some transport equations, and then we applied inverse methods, which is essentially just a variant of an optimization approach to try and tune what the constitutive equations should be in order to capture this behavior.
Okay, so kind of when you talk about increased film thickness, what sort of film thickness differences are you actually seeing?
So we're talking about 20 nanometers up to hundreds. So it's a significant increase in film thickness that we're able to predict and that was observed experimentally.
And do you know how sensitive the model is to kind of the synovial fluid viscosity and things like that? So, in a patient, let's say, normally the synovial fluid is a lot thinner than you get in a person who's around the ages of 20 or 30. And I wonder, I just wonder whether you still get the same effect for those thinner fluids, or those thinner viscosities or lower viscosities, and therefore you would get the same effect in an artificial joint, say.
Yeah, well, it depends a little bit on how much you get this aggregation and how much you predict to get this aggregation at the inlet. But yeah, certainly looking at different patient groups is something that's really interesting. We know that patients that have had surgery or less healthy joints have different kind of different molecules in their joint fluid. So yeah, we would expect, and we certainly predict different film thicknesses. We also see significant changes in film thickness with operating conditions. If we look at cycles and we change our loading pattern, we can end up with a prediction of a sweeping away of this sort of higher viscosity region out of the contact, and then this gradual build up again, and so transient effects, and that kind of hints towards what you could see in a real geometry. So where we have real loading and we have real transients, and how we then go ahead and use that to inform our joint design was, I think that's really interesting, and it's something that would be fantastic to try and do, and something that we're working on at the moment.
Because one of the key things that has arisen largely out of the metal on metal kind of issue that was in the decade from 2000 to 2010, and the consequences are still ongoing, obviously, for the patients themselves, was the idea of clearance. And I presume that the clearance, in this model, perhaps the clearance would be an important parameter.
Well, I think clearance is something that we would predict, and being able to accurately capture the clearance, I think, is one of the things that we want to be able to do. We know that as the radius and the geometry of our joints varies, then we get different points of contact. And we've got another student who's looked at the full knee implant geometry rather than a sort of simplified ellipse or ball on surface kind of geometry. And we can see that there's multiple points, and we get very highly loaded points. We get very large spikes, and coupling these two things together to be able to accurately capture film thickness would be really important, as well as including a mixed lubrication or boundary lubrication model within the predictions.
So do you anticipate design changes then to the kind of bearing, to the kind of, to the, to a joint, or to a knee joint, or perhaps not a hip joint, but certainly, a knee joint, which is a relatively complex design? Could you kind of anticipate a design change to improve overall the lubrication across different scenarios or different conditions?
I guess the short answer is I really have no idea. I don't know. I mean, you could certainly imagine that you could have one if you can predict your film thicknesses really well, and you're trying to optimize your film thickness, or even try and minimize wear. If you have a wear model that's based on a mixed lubrication formulation, then yeah, absolutely, this is the kind of, you'd parameterize your geometry, you'd run it for a range of different loading cycles, and then try and minimize wear. And again, trying to work out what the most important loading cycles is really important as well. And trying to capture the most adverse load and activity is something that would be really interesting, and something that could be used to inform not just the design of the joint, but the use of the joint, and trying to make sure that patients can recover and essentially make sure that their joints last as long as possible.
I suppose one thing that you may want to consider is that that Tony Redman has all this data from lifelong joints, which are various activities. I'm not quite sure how many activities they finally did at the end, but they did it for about 160 patients all told. So something like that put in your model, and demonstrate for different activities would be a fascinating line of inquiry.
Yeah, and this is one of the advantages of having a large consortium like BioTrib and the previous one of lifelong joints. It gives us all of these opportunities. So yeah, we absolutely want to start using real loading rather than a sort of maybe an ISO gate cycle or something that's fairly standard. Yeah.
Mm-hmm, mm-hmm. So going long term or going medium term, the next 5 to 10 years, where do you think, I suppose the first part of the question, where do you think this specific research is going? We talked a bit about the design, but I think, widening up the question around your research field as a whole, what do you think the exciting elements are, both in medtech, but also in aerospace and in kind of tribology more generally?
Okay, so the work we want to expand this work into not just fluid film lubrication. We want to start looking at real, more complex phenomena in the joint. And I think, the inverse methods approaches and optimization and throwing computers at the problem, I think is an approach that I want to look at more. I think we shouldn't be worried about heavy computation and we should see what we can achieve there. And once we can accurately predict wear or tribocorrosion even in a joint, then I think this is where we can start looking at firstly optimization, then optimization for different loading cycles, and then maybe a stratified approach, different joints for different patient ages or demographics, and optimizing for that. And we're seeing this more generally for optimization. We're looking at aerospace, we're seeing greater multidisciplinarity. We're seeing optimization of aerodynamics and structures together in a sort of aeroelastic kind of framework. So we're seeing more and more computationally expensive problems being thrown at optimization to design really challenging engineering devices.
Fantastic. And lastly, I'm an experimentalist. To further this, I presume you need some data around properties and things like that. So what would you want from kind of experimentalists going forward? I presume that their relationship will change, won't it? From, traditionally it's been almost a one-to-one kind of partnership, but now computational methods are so diverse and so good at doing the job. You can design whole plane systems now basically by using a computational approach. But we still need the experimentalists, hopefully, going forward. And I was just thinking, what would you want from an experimentalist to deliver better models? How would you like to populate some of the kind of information that you need to do those kind of modeling processes?
Yeah, so I'm not of the view that computational work is ever going to replace experimental work in the biotech engineering sector or aerospace as well. I think it's computational models apply constitutive models that are being developed experimentally and are based on observations, and it's a computational way of doing something that's a bit more sophisticated, or a more complex geometry, or doing a wider parameter search. But you have to trust your material properties of your bulk. You need measurements of just as we've done with the work of Lee Nissen, looking at the joint fluids. Looking at, we're applying inverse methods, so we're measuring and calculating fluid properties based on experimental work. And I think in terms of what would be really nice to have experimentally is that wear data, the film thickness data, which I know is a massive challenge to obtain, and use it to calibrate and tune our computational models. And I think it's not just about a sort of multi-fidelity approach where we tune and scale our film thicknesses, but it's about working out why our models don't work when compared to experiments, and working out what part of the model doesn't work, and doing better, and maybe a better Young's modulus or a better rheology or something like that to better capture the real physics and try and work out how to design better joints using optimization approaches.
And I suppose what it does as well, it allows you to inform the experimentalist. It allows you to say that, no, this is the experiment that we actually want you to do. And I suppose the first thing is around capabilities, and can we actually perform that experiment? But if we can, then surely that's a kind of good approach. And it reminds me to some extent of how kind of astrophysics works, where you get these large computational kind of models of the universe, and then they go and tell the astronomers to go and try and look for telltale signs that this model is or isn't correct. And I suppose the similar thing is, is going to be seen here, where you get this link, this continual design of experiments that's done computationally that then we have to go and do, as it were, as experimentalists.
Yeah. There's always a comment about astrophysics when talking to you, Richard. But I agree. I think that it has to be a collaborative approach. One of the one of the major advantages of computational methods is that you can say, yeah, this model works, and we've calibrated it on a few variables and a few things that we can measure. But actually, because we trust our model, we can now probe things that experimentally just simply can't be explored. So I think it's a partnership, and it's about working out what can be measured experimentally and what can't, and how do we test that the model works, and then really exploring the problem in more detail. And actually, for me, that's also, when it comes to optimization, I think it's not just about having a final design that works better. It also often tells you about the physics. It tells you where the compromises lie. Because in optimization, it's all about, if we increase this radius, what happens to the fluid, and what happens to the contact pressures and things like that. And we get to understand the physics a bit more, even when we apply optimization onto models that we maybe trust already and have validated already. So I think there's just a wealth of really interesting results that we can tap into using a combined experimental and computational approach.
Okay, thank you, Rob. That's I think a good point to end the kind of discussion on. And I'd like to thank you once more for your contribution and agreeing to do this interview, as it were. So thanks very much.
It's good to talk to you. Thank you.